All right. So we kind of switched gears on Monday, and we started building up some ideas around term-by-term integration to approximate integrals asymptotically. And then we also introduced the idea of integration by parts. So,
Zach, can you reshare? I'm getting the long, skinny white rectangle.
oh, weird. Okay. Is that working?
Yep, that's better.
Okay, sorry about that. Okay. So last time we talked about term by term integration asymptotics. And we said the basic idea is that you can Taylor expand the integrand and then integrate each term. So integral from a to b of f of x dx equals, or is asymptotically approximated by integral from a to b of the sum n equals 0 up to infinity of, let's say, fn, and then x minus x0 to the nth power dx. Okay. As long as boundedness constraints hold on expansion, right? And expansion exists, okay? But may not be very accurate, okay? And the point is you can do this, and it's straightforward, and it'll work. And remember, we talked some about different boundedness conditions of the function within your domain of integration. If you're integrating out to infinity, obviously you need f to fall off quickly enough that the integral exists. You need the integral to not involve some blow up that's going to give you an infinite integral in the interior. But this may not be very accurate because as you increase x, okay, you are only sort of building up these algebraic corrections as you add more and more terms to the asymptotic series. And oftentimes you can get more transcendental corrections that are more consistent with the sort of flavor of the integrand by performing integration by parts. And so integration by parts can give approximations that are more tailored to the specific integrand, okay? And so importantly, what happens then is that if you have some integral from a to b of some function f of x dx, right? If we write this as the integral from a to b of some separate function a of x, f of x, a of x dx, right? Then we can always split this integral up then into the integral of a dx, right, times f divided by a. So I'm using a twice here. Okay. Minus the integral from a to b of integral of a of x dx. Oh, sorry, other way around here. I'm going to integrate up this part and differentiate this part. Okay. Okay. The a dx integral from f of x over a of x dx, and then this whole thing is integrated. Okay.
Should that first dAdx just be a?
Yeah. Yep. Okay. All right. So, standard integration by parts. The point is, though, if we take this part to be I1 of x, and this part to be I2 of x, to be effective, what we want is that I of, sorry, it's not necessarily a function of x, it's just I1 and I2. I1 needs to be much larger than I2, okay? And this is our asymptotic assumption, okay? All right, so integration by parts, right? What's the idea? It's essentially that you split this up in some clever way that allows you to generate an accurate approximation using this first boundary term here, and then some subsequent interval that's significantly smaller. It's of smaller order, and this is a recursive way then of generating asymptotic series. If you can do this repeatedly and always generate a smaller integral term in the next integration by parts. And we'll talk about a few different methods for doing that, and then we'll move to sort of other adaptations of integration by parts that work for specific forms of integrals. And so in general, for our term by term integration, right? A generalization of the definition that we wrote down yesterday, or sorry, on Monday, is if the following holds n equals 0 up to infinity, fn of t phi n of x, okay. If this holds uniformly on the interval t goes from a to b, and each fn of t has a measurable, is measurable in t, and h of t is integrable in t, And the integral from a to b, h of t fn of t dt exists, then we can also consider integrals of the form h of t f of xt dt. It exists for each x in some neighborhood of x0, and the integral from a to b of h of t f of x t dt is asymptotically approximated from this as the sum of these coefficients phi n of x, integral from a to b, integral of h of t fn of t dt as x goes to x0. Okay. And so again, this is, some assumptions that we need in order for term by term integration to hold. This expansion of the integrand needs to hold uniformly. Okay. We need for these coefficients to have measure, and also to be able to take that integral. So we've sort of built up a lot of definitions. Let's look at an example. So if we want to look at the following integral now, and let's say that we look at it in the limit as x goes to 0 from above. Okay. So a typical sort of integration by parts of this will not give us a nice closed formula. But notice that we have an integrable singularity, f of t, sort of scales like 1 over t to the 1/2 as t goes to 0 from above. And this is convergent, right? Because when I integrate it up, I can evaluate at the boundaries. So if we just call f of t the integrand here, and we note that we can expand the exponential using just a Taylor series about 0, because our domain of integration, we know, is going to be close to 0 because x is close to 0. Okay. This is going to be uniform for t in 0 to a for all a greater than 0. So now if we apply our result from before, I of x is going to be approximated by the series, okay, given by the sum from n equals 0 up to infinity, minus 1 to the n over n factorial, the integral from 0 to x, t to the n minus 1/2 dt. We can take all these integrals and evaluate them. And we get that this is equal to the sum from n equals 0 up to infinity of minus 1 to the n, x to the n plus 1/2 divided by n factorial and n plus 1/2. Okay. And because the integrand's radius of convergence is infinite, we also have a radius of convergence of infinity for this, and in fact the sort of approximate asymptotic series can be replaced by just an equals sign, because we have an infinite radius of convergence, and so it's not an approximation if we take this all the way out to infinity. Okay, so this is our term by term approximation. We could truncate this series to 1, 2, 3, 4 terms and see what our order of approximation is. Okay. Alternatively, we could consider the integration by parts approach. Okay. So if I consider integration by parts, integral, I'm going to rewrite the integral as, first of all, the integral from 0 to infinity minus the integral of x from x to infinity of that same integrand t to the minus 1/2 e to the minus t dt. Okay, and we can compute this integral. It's just given by the gamma function evaluated at 1/2. In other words, the square root of pi. The remaining integral now is going to be the one that we use integration by parts on. Okay, and so when I perform integration by parts, I get I of x is equal to square root of pi, okay, plus the integral from x up to infinity of t to the minus 1/2. And I'm going to write the derivative of e to the minus t there. Okay. If I differentiate this, right, I get that minus sign back. I'm just setting this up for integration by parts, and I end up with square root of pi e to the minus x over square root of x, now plus 1/2 the integral from x up to infinity t to the minus 3/2 e to the minus t dt. Okay, and so so this works, and it gives me some result, right? But notice that this term here, right, I'm going to get some square root of pi, right? And then I'm going to have e to the minus x over square root of x. Now, the limit of this as x goes to 0, right, is going to blow up, okay? If I look at what I get from this, I'm also going to have a term that blows up, right? So I've sort of chosen wrong in this case, okay? Integration by parts does not work for this particular choice of splitting up the integrands, okay? Because one of the limits blows up, okay? And I have a singularity at the boundary, okay? So that can happen, right? And these that's why you have to sort of take care when you're choosing how to compute your integration by parts, and how you split up your integrand in this case. Okay, so we're gonna dissect that a little bit more, before we go through some more examples, I just want to talk a little bit about the taxonomy of integrals that you may come across. So one thing to notice here, right, is that we have some factor here out in front of our exponential. But in order to, do the integration by parts here, even though it didn't work out well, right? If you write things in terms of some exponential and then everything else, then you have a natural function that you can try to be the one that gets integrated in the integration by parts process. So you can take, through the chain rule, the derivative of the argument of your exponential, okay? Take that from the other part of the integrand, and then whatever remains, you just differentiate that part, okay? So that's often how we think of integrands when we talk about asymptotic methods for integration. So that sort of brings us to different classes of integrals, okay? And each different class of integrals gives us a different sort of set of methods we might use. So one of these we call Laplace integrals, and these can be written in the form e to the x phi of t dt, okay? And x lives in R, okay? Phi is some real function where it gets mapped to the real numbers, and f of t could possibly be complex, okay? That's a Laplace type integral. A Fourier integral, as you might imagine, is one that comes from Fourier transforming. So there we have f of t e to the I x psi of t dt, okay? And so here we have phi and x are real, okay? F of t can be complex. We also have contour integrals where I of z is an integral over some contour h of t e to the z rho of t dt. Z and rho are complex, and h can be complex, and c is some curve in the complex plane. Okay. So each of these different types of integrals leads to different techniques, okay, in terms of the asymptotics that you might try. A Laplace integral, you can try integration by parts. You want to make sure that you take the correct split of your integrand, okay? The Laplace method, okay, is the alternative approach, and that's sort of the second approach that we'll get to after integration by parts. Fourier integrals, you can also try integration by parts, as well as a method that we'll call stationary phase, okay? And lastly, for contour integrals, we'll use what's called steepest descent, and we'll cover that after those other two methods, okay? So the integral that we sort of just saw was a Laplace type integral, right? We had fixed x to just be, 1 in that case. So we can talk about in general how to handle integration by parts for Laplace integrals, right? Because we have this formulation, we can write how you might try splitting things up in order to perform that integral, okay? So if I go to integration by parts for Laplace integrals, what's that going to look like? Well, I have some function I'll call I of x, which is defined as my integral, f of t, e to the x, phi of t, dt, okay? Let's say, for example, x goes to positive infinity in this case, and phi is 0, okay? Well, then we can write phi I of x in the following way. F of t divided by x phi prime of t and d dt of e to the x phi of t dt. So this is now sort of naturally split up into the derivative of the exponential term, and then the term that would come down from the chain rule, what I have to sort of cancel out from this additional term in the integral grand, okay? Now, integration by parts, what it's going to yield in this case is e f of t e to the x phi of t, x phi prime of t, t evaluated between a and b, and lo and behold, okay, I get a minus 1 over x popping out in this case, okay? Now, since x is going to positive infinity, okay, this works out well because I have something that's going to be vanishingly small as x gets larger and larger, okay? On the interior of the integral now, I have d dt of f of t over phi prime of t, and then I just have e to the x phi prime of t left inside, okay? If the second term is much less than the first term, as x goes to positive infinity, then what I can say is that I of x is going to be asymptotically approximated by 1 over x, right? So I have this 1 over x term here. F of t e to the x phi of t divided by phi prime of t evaluated between a and b in this case. So now I have what's called a leading order approximation that I've gotten by just performing this integration by parts and inspecting the boundary terms, okay? This, we'd have to sort of do another integration by parts and show that the associated leading order term was that, sort of adds another factor of 1 over x, right? Or you can do your own sort of bounding process on this integral in order to show that this term here is going to be asymptotically smaller than this term, okay? But in general, okay, this works if phi prime and f are continuous in a to b, and phi prime of t is not equal to 0 in A to B, okay? Because otherwise you're going to run into problems here, okay? And f of A is not equal to 0, or f of B is not equal to 0, okay? It turns out if phi prime is equal to 0 in A to B, we're going to need another method, which we call the Laplace method, okay? So integration by parts, though, you can generate the leading order approximation. You can also generate a remainder term, right? Which you can get from term by term expansions, right? But note here that sort of whatever form the integrand has, that's going to show up in this leading order approximation. And so it's going to be sort of much better fit to your particular integral than just an expansion in a power series, okay? This term here is going to serve as your remainder, or you can just repeat this integration by parts process in order to generate further terms in your expansion. Okay. Let's take another example. So let's say that I have I of x is equal to the integral from 0 to infinity of e to the minus xt, 1 over t dt. And I want to compute this in the limit as x goes to infinity, okay? So what I have here is that f is equal to 1 over 1 plus t. And I have that 5 is equal to minus t. Now, if I integrate by parts, I get 1 over x minus 1 over 1 plus t e to the minus xt evaluated between 0 and infinity. And then I have this additional term, 1 over x integral from 0 to infinity, e to the minus xt over 1 plus t squared dt, okay? So I can simplify this a bit, and I get just 1 over x minus 1 over x integral from 0 to infinity, e to the minus xt over 1 plus t squared dt, okay? Now, if I integrate by parts n minus 1 times, what I get is that I of x is equal to 1 over x minus 1 over x squared plus 2 factorial over x cubed, so on and so on, minus 1, n minus 1, n minus 1 factorial over x to the n plus some remainder term, okay? So I'm getting some power expansion here. My Rn of x I can show is big O of 1 over x to the n plus 1. So that means that I of x is approximately equal to 1 over x minus 1 over x squared plus 2 factorial over x cubed plus minus 1 to the n minus 1 n minus 1 factorial over x to the n, okay? So, so integration by parts, right, it leads me to this sort of power series in negative powers, okay? A more general result, though, for an integral like this is if, let's say, I of x is equal to the integral from a to b of f of t e to the minus dt xt dt, okay? And we say that let's say a to b is finite, f is continuously differentiable for the first n plus 1 derivatives, okay? And we also say that f is going to be piecewise continuous up to the n plus second derivatives, okay? Well, then, in general, okay, I can, for any integral of this form, I can sort of write out the general integration by parts formula that we get. And that's that I of x is asymptotically approximated as n equals 0 up to n e to the minus xa, x to the n plus 1, f's nth derivative evaluated at a, okay, as x goes to positive infinity, okay? So it turns out in this case, there's no contribution from b, from the right endpoint. Why is that? Well, because e to the minus xb is going to be much less than e to the minus xa over x to the n, basically for all n in this case. All right. So that's a nice formula then that holds for a broad array of possible Laplace integrals, right? As long as you just have this, sort of constant exponential term up here, okay? E to the minus x times t. Sorry, just that term e to the minus xt. Now, for other integrals, right, you have to go through the procedure of performing integration by parts. Let's do one more. I of x, let's say, equals the integral from 1 to 2 of e to the x hyperbolic cosine of t. And let's take that as x goes to positive infinity, okay? Well, again, integration by parts, our integration by parts approach tells us that we can split this up into whatever the chain rule differentiation of this would be, right? And then the remainder that we get from that in the integrand. If we do that, then we perform one step of integration by parts, then we get e to the x hyperbolic cosine of t divided by x hyperbolic sine of t, evaluated at the boundaries, okay, plus some remainder term, okay, that we'll leave aside for now, e to the x hyperbolic cosine of 2x hyperbolic sine of 2, and this holds as x goes to positive infinity. And we drop the other term in the boundary because e to the x hyperbolic cosine of 2 is going to be much bigger than e to the x hyperbolic cosine of 1, because x is diverging to infinity in this case. Okay. Now, so in general, just to sum up, right, this integration by parts formula, right, you can generate as many terms as you want, right? Oftentimes it's good enough to just take one or two terms, okay? And you can use sort of boundedness arguments in order to make claims about the integral remainder, or you can inspect sort of the prefactors that come out as you're performing integration by parts. Okay. For Laplace integrals, there's sort of a natural way to split up the integral by parts, right? It's just sort of performing this chain rule differentiation on this, see what the factor is, and then dividing that out from the remainder of the integrand. If this doesn't work for your particular integral, you may either have to rewrite the integral, sort of split it up, or make a change of variables. And so we'll talk about that more as we start to look at other integrals in integration by parts. Yeah, I think the next thing I want to talk about is moving over to Fourier integrals for integration by parts before we get into Watson's lemma and Laplace method. Let me take a quick breath and ask if there's any questions so far about this integration by parts procedure.
So this Laplace's method is just integration by parts on integrals of this specific form, and they have this nice result where we can drop.
No, we're still talking about just applying integration by parts to Laplace integrals.
Okay.
So yeah, so you can use two approaches, and we're just talking about applying integration by parts to Laplace integrals. I still haven't told you what Laplace's method is, so that's kind of the next lecture. We're still sort of in integration by parts, which I think will probably feel fairly familiar and maybe intuitive for now. Okay. Integration by parts, we're still talking about it. What if we apply this to those Fourier integrals that we wrote down before? What's a Fourier integral? Okay, it sort of looks like a Laplace integral, but it has an imaginary exponential instead of a real exponential. Okay. And let's say that x is large in this case. So we have a highly oscillatory integral, okay? So let's think about what that does, right? As this function changes just a little bit, you have very fast oscillations in your complex exponential. So the idea of an asymptotic approximation is that somehow you kind of average over those oscillations in order to get something to leading order, okay? So the Riemann Leba lemma, okay, is going to offer some help with this, okay? So the restrictive form of the Riemann-Lebesgue lemma says that if f is L1 from A to B, then the integral, right, of the absolute value of f of t is bounded, okay? Then the integral from A to B of f of t e to the I xt dt goes to 0 as x goes to positive infinity, okay? and it doesn't require smoothness of f. So let's think about why this is, right? The faster this thing oscillates, right, the more you're just going to have integral contributions that are right next to each other that are of the same amplitude, okay, but different sign because you have this oscillation here. And they're going to always cancel each other out, okay? You're integrating against this oscillating function, right? Think of a sine function if that helps. Everything's going to get canceled out in this case once that starts oscillating quickly enough, okay? Now, a more general form of Riemann-Lebesgue is if f is L1 from A to B, and psi of t lives in C1 from A to B, okay? And we say that phi of t is non-constant, okay, on any sub-interval of A to B, then the following thing is true. The integral from A to B of f of t e to the I x psi of t dt, okay, is going to go to 0 as x goes to positive infinity, okay? So now this doesn't just have to be t, it can be sort of any function psi of t as long as it's non-constant and continuously differentiable, okay? So this really allows us to now think about asymptotic approximations that have sort of vanishingly small leading order terms and then sort of even smaller next order terms as we move through integration by parts. Let me just write that out in general, and then I think next time we'll have to start with some examples, okay? So in general, right, integration by parts for these Fourier integrals, we can think of the integral from A to B of f of t e to the I x psi of t dt, okay? I can write this as 1 over ix f of t over psi of t e to the ix psi of t evaluated between A and B. And then I have this additional term 1 over ix integral from A to B f prime of t psi prime of t, okay, e to the ix psi of t dt. And this thing here, right, is big O of 1 over x. And this thing here we'll claim is little o of 1 over x, as long as the following thing is true if f prime of t and psi prime over psi prime of t is continuous and L1 from A to B, okay? So I of x is then to leading order 1 over little I x f of t divided by phi prime of t e to the I x psi of t evaluated between t equals a and b as x goes to positive infinity, okay? And we need that f f prime over psi prime are L1 1 from A to B. We need that psi is C1 from A to B. And we need that psi is not constant on A to B. Okay. So again, these Fourier integrals, right? You sort of use the same approach here. We're going to have, sorry, need a prime there. We need the factor that comes down from chain rule differentiation of this, so that we can integrate this up. We divide through by this, right? And then we differentiate this function in order to get our integrated up, our next term in our integration by parts. As long as we satisfy some assumptions about this integrand, then we can show that this additional term here is going to be little o. And then the leading order term here is going to be of order big O of 1 over x. Okay. So this works as long as this x goes to infinity. And that's because of this sort of generalization of the Riemann-Lebesgue lemma. The exponential term is oscillating fast enough that you get sort of cancellations of most of the integral. And this is just the kind of leading order part of that. And then everything is going to be smaller. Okay. So that's Fourier integrals. And that's sort of the general theory of integration by parts. I think what's helpful, though, is to just sort of go through a couple more examples. So we'll start lecture on Friday by going through another example of integration by parts. There's some practice problems on the homework as well. And then we'll talk about moving away from integration by parts to Laplace's method and what's called Watts's lemma. Any questions before we stop for today? All right. Well, yeah, okay. So homework 2 is posted. That's going to be due a week from Friday. I should have your homework 1 marked by Friday. So stay tuned on Canvas, and you'll see some feedback, and the speed grader and your grades will all be up in Canvas as well. Okay. Well, I'll see you on Friday, if not before then.
Thanks, Zach.
Thanks. Yep.
Thank you.